kick off our unit on thermal physics, we're going to start by defining a couple terms that we'll use throughout the unit. And those words are heat and temperature. Now, both of these words are used almost interchangeably in our everyday lives, which makes it that much more important that we can tell the difference in the world of physics. So let's start by tackling this quantity of temperature. If we're talking about what temperature is, typically we're referring to how hot or cold something feels to us. Now, that's often a pretty relative measurement. If I said that something is hot, it feels hot, it's typically just meaning that the temperature of the object is hotter than my body's temperature. If it feels cold, it's just colder than my body temperature. But in physics, it's more important that we can quantify this. And you can often probably already think of different units that you use to quantify. Either if it's in Fahrenheit or Celsius or even in Kelvin. You are quantifying exactly how hot or how cold something is. But if you really think of it, that has to have some sort of physical meaning as well. That when we actually measure temperature and talk about what it is, what we're really referring to is how fast molecules are moving. That the temperature is the average kinetic energy of the molecules of a substance. Now, it's harder for us to imagine sometimes what the molecules are doing around the substances that surround us, but all objects around us, or all substances, have molecules in motion. It's a little easier to imagine the air or the gas around us, those molecules zipping around, or liquid like the liquid in my lava lamp behind me. But it's a little harder for us to imagine in a solid that molecules are moving as well, that those molecules are just vibrating back and forth in place. And the speed at which they do that tells us essentially what the temperature is of that object. So average kinetic energy, we've seen before, 1/2 times the mass times the velocity squared. Not every molecule in a substance is going to be moving the same velocity. So taking the average of all these velocities is essentially where our temperature is going to come from. And we'll calculate that a little bit later on in this unit. We can actually calculate how fast different molecules are moving at different temperatures. But right now, just know that the faster particles move, the more the temperature in that object or that material is increasing. So if we look at two different samples of an object, one where the particles are moving slower and one where the particles are moving faster, shown here by vectors, we know that the hotter object, the higher temperature, is the one with these molecules moving faster, assuming that all the molecules in these two pictures are roughly the same mass. So if we look at two samples here in the desert, that everything's come to equilibrium, it doesn't matter how big or how small a rock is, both of these rocks internally have molecules that are moving at the same average velocity. We can say that then they have exactly the same temperature. That there is no difference in the temperature for these rocks because they have each come to an equilibrium with the air temperature, so those molecules are moving around faster. That the larger rock wasn't hotter, the smaller rock wasn't hotter. The rate at which they change their temperature is going to be different, but given enough time, they have exactly the same average kinetic energy. So when we quantify these temperatures, as I alluded to before, it is important that we have units to help us define exactly what temperature an object is. And we'll relate that to velocity and mass later on. But right now, let's make sure we have a good grasp of these units. Two very important temperatures that we base our scales around are water boiling and water freezing. Water is a very important substance in our lives here on Earth. So these temperature scales are kind of built on that. That in Celsius, water freezes at 0 degrees. You might also be familiar with that being about 32 degrees Fahrenheit. In Celsius, water boils at 100 degrees. And in Fahrenheit, you might know that that's 212 degrees. Now, notice how there is a 100-degree span between water boiling and water melting, or water freezing. That this is not a coincidence. The Celsius scale is built off of this nature of water. That 0 is defined as when pure water freezes, and 100 is defined as when the water boils. And then there's just increments of a 100, splitting that up in even increments. Fahrenheit is designed a little bit differently. It's useful for a lot of things, talking about how hot or cold something feels to a human, but not as interesting for us in science. So we're often not even going to think about Fahrenheit in this class. You might also notice that there's another temperature that's located here on these scales, and that is labeled absolute zero. That there is a coldest possible temperature, and that absolute zero gives us our third temperature scale, known as Kelvin. Kelvin is defined based on this coldest possible temperature. 0 Kelvin is absolute zero. You can never get colder than that. And Kelvin is just an offset of Celsius. So notice here that there are 100 Kelvin in between water freezing and water boiling, just like Celsius. But water freezes at 273 degrees Kelvin, which means that absolute zero for Celsius is negative 273. This is going to become important for us later on, but you should be able to relate these two. Looking at these three scales, though, if I were to ask you something like which temperature scale is most precise, the answer isn't the obvious one. We think the one with the biggest numbers often is the most precise, but precision is a matter of how small of increments you get, how fine-tuned your measurement is going to be. And technically, Fahrenheit has the smallest increments. So Fahrenheit is more precise than these other two. But if we look at which temperature scale an increase of 1 degree would be the largest, well, water freezing and water boiling both have 100 degrees between them for Celsius and for Kelvin. So we would say that that has a larger increase for each degree. Notice here that a change in Celsius is going to equal the same as a change in Kelvin because they have the same increment size. So to reference this idea of absolute zero again, at absolute zero, the reason that it is our coldest temperature is because of those molecules moving. Again, as I mentioned before, an object, even if it's a solid, those molecules are vibrating. They have a kinetic energy. Their average kinetic energy tells you their temperature. Well, if they stopped vibrating, they no longer have any kinetic energy. That is the lowest possible temperature, is when those molecules stop moving. Now, that doesn't occur anywhere in our known universe. There is no example of absolute zero happening. We've gotten very, very close to that. Actually, some of the coldest places in our known universe are in labs here on Earth, with the goal of getting as close to absolute zero as possible. But it is almost impossible, as far as we know, to fully stop those molecules. It is kind of this limit, but not something that we have examples of in nature. So as I mentioned before, Kelvin and Celsius are just offset of each other, and that offset is 273 degrees. The IB Physics data booklet gives you this conversion factor, that temperature in Kelvin is just Celsius plus 273. That means if you wanted to go from Kelvin to Celsius, you subtract 273. So 233 degrees Kelvin is negative 40 Celsius. 0 degrees Celsius, when water freezes, that's 273 degrees Kelvin. So with that in mind, 295 Kelvin is what in Celsius? Taking this equation in mind, 295 minus 273, you end up with 22 degrees Celsius. That's about room temperature, is almost 300 degrees Kelvin. And then water boiling is 100 degrees Celsius. What is that temperature in Kelvin? We saw this on the scale earlier, but adding 273, you end up with 373 degrees Kelvin for water boiling. A couple memes that I enjoy here, looking at temperature scales. Fahrenheit is really useful, talking about comfort level for humans. 0 is really cold outside, 100 is really hot outside. But Celsius would be 0 is fairly cold outside, 100 is dead. And then Kelvin, of course, is dead. 100 degrees Kelvin is still very, very cold. That's 173 below 0 for Celsius. Also, did you hear about the man who got cooled to absolute 0? He's okay now. So if we think about temperature then, how fast on average the molecules are moving, doesn't matter how many molecules we're talking about, it's just their average speed, their average kinetic energy. So the one that has a higher temperature is the obvious answer here, a burning match. These molecules are moving much faster than something that is cold, like an ice sculpture. All right, let's shift gears and talk about a little broader category here. So we've referenced temperature. That's one way that we'll define the thermal nature of an object. Another way is by looking at its total internal energy. Temperature is one part of this. Internal energy is represented E with a subscript of INT for internal, and that is made up of two main parts: kinetic energy and potential energy. And this is talking about the energy of the molecules themselves. The kinetic energy is what we just talked about. It's really the temperature of the molecules, or the temperature of the object. The higher temperature, the faster the molecules in the object move, giving it more kinetic energy. Potential energy is actually a reference to the state of matter that that object is. We're going to reference this a little bit more when we get into phase changes and a phase change diagram. So maybe keep this in mind for later on. But potential energy is state of matter. Kinetic energy is the temperature. The total internal energy is both of these combined. So if we look at total internal energy, here we've got a large rock and a small rock. We said that they both had the same average kinetic energy, but their total energy now depends on how many molecules there are. That if they're both moving, these molecules are moving at the same relative speed, but one object has a lot more molecules, its total is going to be a lot bigger because you're adding that energy more times. You're adding it for every molecule that there is. So we say that the larger rock, in this case, has a higher internal energy because it's looking at the total energy now, not the average kinetic energy, the total kinetic energy. So more mass gives you a larger total energy. With that in mind, it is also counterintuitive here, but a burning match, ice sculpture, an ice sculpture has more internal energy. In this case, each molecule has a lower kinetic energy than the burning match molecules, but there are so many more molecules that if you total them up, a lot of little energies adds up to more than a few large energies. So an ice sculpture, because it has so much more mass, has a larger total energy. And one way to think about that, just to come back to it, if you imagine just the size of something, if you were trying to heat it up, the larger it is, the more energy it requires to change. We'll get into that a little bit more in our next topic when we talk about specific heat, but mass is a huge part of the amount of energy that is contained in an object. The final piece that I want to reference here is heat. Heat and temperature, as I mentioned before, are often used kind of together when we talk about how hot or cold something is. But heat is related to that thermal or that internal energy. Heat is the transfer of this energy. So when we talk about heat, we're always referencing energy being transferred from one place to another through this thermal nature. It always is going to flow from hot to cold. So if you have a hot chocolate, the energy flows outward to the surroundings. If you have ice water, the heat energy flows into that ice water. It always will flow from hot to cold. So if that's the case, if you are holding an ice cube, one of these is correct. Heat flows from the hand to the ice cube, or heat flows from the ice cube to the hand. One of these makes your hand feel cold. And in this case, it's tempting to say that the ice cube is making your hand feel cold because it is transferring this cold energy to your hand, but that is not what's happening. Instead, heat is still flowing from hot to cold. It's flowing from your hand to the ice cube. The reason your hand starts to feel cold is because it is losing some of that energy. That those molecules in your hand are starting to slow down and get colder because the heat is flowing away. And the reason that heat flows from hot to cold, if you imagine on a molecular level, if you have two materials next to each other, one that is hot and one that is cold, the hotter object has a higher temperature, so the molecules move at a higher kinetic energy. They're moving faster. If they collide with molecules that have a low temperature, it is going to speed them up. It's basically giving them a boost. In the process, these hotter molecules probably lose a little bit of their energy because it's transferring some of that energy and that momentum to the lower temperature molecules. So these fast moving particles, they collide and then they transfer it to increase the velocity of the object that is lower temperature, which then makes it hotter. And then finally, I just want to stress that energy is energy. We've talked about energy before in this class. We've talked about kinetic, potential, elastic, and we'll talk about energy further on in this class as well. But all energy can be converted from one to another. When we talked about energy being conserved, the key thing that kind of threw us for a loop sometimes is when friction was involved and started to transfer some of our kinetic and potential, our mechanical energy into heat. It was kind of lost to nothing. But sometimes that's exactly what you want. If you take kinetic energy, you can create thermal energy. So here is one of my favorite examples. This guy is taking a hammer to transfer the kinetic energy of that hammer into thermal energy in this steel. Now, kinetic energy is just calculated 1/2 times mass times velocity squared. This hammer certainly has a lot of mass, and it has a lot of velocity when he strikes that. And that energy has to go somewhere. Some of the energy is going to the sound that you're hearing. So that sound energy is happening because of that collision. But a lot of that energy is being converted into heat in that collision. And right now you can't see it a whole lot. But as he continues, that heat, that transfer of energy, starts to increase the temperature of this steel. And you can start to see just a little bit, that steel is starting to glow red hot. That thermal energy is becoming visible. And there's so much thermal energy that he's then able to light this piece of paper on fire, which is the most amazing way to start a fire. This can also be used for some fun thought experiments. One that went viral not too long ago on the internet was this question here. If kinetic energy is converted into thermal energy, how hard do I have to slap a chicken in order to cook it? Because your hand has mass and has velocity, that energy can be converted into heat to, in theory, cook a chicken. So the main takeaways for this lesson, you should be able to describe the relationship between temperature and kinetic energy of those molecules. You should be able to describe the energies present in an object's total internal energy, so both kinetic and potential, and what each of those represent. You should be able to convert between Celsius and Kelvin using that 273 degree offset. You should be able to describe the nature of molecules when something is at absolute zero and what that actually means. And then describe the difference between these words of temperature, internal energy, and heat.